All right, welcome back. This is another lecture in Descriptive Physics, and today's topic, or this topic, is going to be sound and music. So the previous lecture was all about waves and vibrations, how vibrations and materials lead to waves, and we talked a decent bit about sound in that lecture, because sound is a type of wave. Hopefully you recall it's a longitudinal wave in air. So we talked a little bit about it. We're going to go kind of dive more into it this time, and see how that extends to what we think of as music. So, the origins of sound. Like I said last time, sound is a wave, and it's produced by vibrations of materials. This is a good example of how vibrations produce waves. A couple of examples are when you say hit a drum head, right? The drum head vibrates up and down. Whole top of it's going to vibrate up and down, and that vibrating is actually pushing, compressing and decompressing the air beneath it, above it, and that compression and decompression, or rarefication is the term, is what produces this oscillation, this wave, this sound wave in the air, and we hear that difference in pressure as our sound. So similarly with a tuning fork, if you strike a tuning fork, then what's happening is you don't usually see it because the movement is very small, but the forks, the two forks of the tuning fork, are vibrating back and forth, and it's that vibration that's actually pushing on the air, compressing and decompressing the air around the tuning fork, which creates these compression waves, these longitudinal waves. And again, we perceive as sound as long as it's in that right frequency range. Similarly for things like string instruments, a little bit more complicated because it's not actually the string, right? The string is vibrating, or when you pluck, say, a string, that vibrates. It's not the string directly that's creating the sound. That string, at least in the acoustic instrument, ends up vibrating the body of the guitar, so the resonant cavity of the guitar, and that vibration is actually what produces those compression waves that emanate out of the resonating cavity. So let's get a little bit of a picture, maybe. Again, we don't really see sound because we don't see the air. The air is made up of particles that are too small for us to see. So it helps to actually just draw out some visualizations and really emphasize the particles that make up the air. So in this picture, we say have a tuning fork, right? And the tuning fork's been struck. So the forks are vibrating back and forth. And we're kind of imagining you put the tuning fork next to like a column, or this kind of cylinder, and we could visualize the sound waves as this longitudinal wave inside of the cylinder, where it's made up of these areas of compressed air, where the pressure is greater, and so where all those molecules are more compact, and these decompressed, or the technical terms, the rarefication areas, where it's much lower pressure. So let's look at an actual visualization in a second here, or a moving visualization, but we want to imagine that when the sound wave is propagating, right, it's not just a freeze frame, these air particles are oscillating back and forth. Being a longitudinal wave, the stuff that makes up the wave, air in this case, is actually moving parallel to the direction that the wave is traveling. It's not that, say, an air molecule on the far left side is making its way to the far right side. It's actually moving constantly in one direction. The air molecules themselves are just oscillating back and forth, sort of, not in place, but in the same area. And the tuning fork is creating these compression areas, and that compression propagates out away from the tuning fork. So that's the wave the wave is the movement of those compressions and decompressed areas, but the particles that make up the wave are just moving back and forth kind of in the same spot. So let's look at the moving visualization here. So yeah, so this is just that same kind of tuning fork, and again, the movement of the forks here is very much exaggerated. When you hit a tuning fork, the movements are quite small, right? But if you really exaggerate them, you kind of get a better idea of what's happening with those forks. So as the forks sort of push outward, that's when we get that compression region, right? You're compressing the air right outside of the tuning fork, and that compression is essentially what's traveling. That's the wave. But any of the particles right next to it, say the tuning fork moved out, it would push a particle out this way and compress with all the other air next to it. But then as it moves back in, that particle moves back towards where it was. So the particles that are making up this wave are actually kind of just going together with this tuning fork. And that overall sort of area of compression is what travels away. Okay, so it's an interesting sort of demonstration of how sound is a wave that needs a medium, right? You need to have air in order to be able to actually hear the sound, or hear any sound. What you can do is actually take, say like a cell phone, and place it inside of a container, and a container that you can actually pump the air out of, so you can essentially create a vacuum inside of that container. And what you'll find is that if you pump all the air, or most of the air at least, out of that container, then if the cell phone is ringing, you're not going to hear it. Or maybe, I think in the example, or in the demonstration I'm going to show you in a second, they're just playing music with the phone, but you don't hear it when that cylinder, when that container is under a vacuum, or has all the air pulled out of it. And the reason is, when there's no air inside that container, the sound that your phone is trying to make, right, it has a little speaker, and that little speaker is kind of oscillating back and forth, but there's nothing there to hit, so there's no air molecules that it can start to move, and there's no way to actually create a compression wave there. There's nothing for that wave to travel through. This is sort of in contrast to a different kind of wave, which we'll talk about more in the coming lectures when we talk about electricity and magnetism, which is a light wave or a radio wave. Both of those are examples of electromagnetic waves. So even though you pump all the air out of this container, you still see that there's a cell phone in there. Right? So that's actually showing you that electromagnetic waves, or light, will travel into that container, out of that container, and even though there's no air in there, there's no stuff to propagate through, the light is fine to just keep going. It doesn't need a medium to propagate through. And similarly, just another example of electromagnetic wave, a radio, so you could still call that cell phone, and you could see that it would light up and it would start ringing, meaning that the radio waves that are being transmitted to that phone are also getting through that vacuum. They don't need the air to propagate through. So what we're going to see here, this teacher has this cell phone inside this container. The container's been pumped down, so there's very little air left in the container. It's basically a vacuum inside. You see on the screen it says, "Can you hear the music?" And you won't hear anything because the container is evacuated. Right? There's no air inside of there. But pretty quickly he's going to pull that stopper out, and what happens is essentially it's weird, or very interesting, where you sort of hear the sound escaping, and then, or you hear the air escaping, and then you start to hear the music.
I can't hear the music.
So no music now. He's going to pull the stopper.
Oh my God!
Okay.
There you go.
Oh my God!
So I would encourage you to go and just watch this video on your own, because I don't know how well the volume's going to, that sound is going to come through this recording. But if you do go and just listen straight to the video, it's very interesting, because you can literally hear that. You hear the sound, that hiss of the seal breaking, so the vacuum breaking, and then you slowly start to hear that music playing, because now there's air in, it's funneled, the atmosphere has pushed air into that container, So now there's a medium in there for the sound to propagate through, and so that sound can actually come out and you hear the music. Okay, so how do we distinguish between sound, which is air, it's a movement of air in some sense, and just plain old wind, right? Because you'll probably know wind is just movements of air, but wind doesn't generally create sound because wind is actually more of like a bulk sort of movement of air molecules. So you actually have air molecules that maybe start over here and are flowing over to somewhere else. Whereas in sound, it's not actually a big chunk of air that starts to move from one place to another. It's areas of compression that are propagating through that air. And again, the air molecules themselves are all just kind of moving back and forth. But once you compress one side of it and then pull it away, then these molecules per second are a little bit more compressed. And then that compression movement, those move back, and that compression keeps moving along. So the air molecules over here are a little bit more compressed, and the air molecules over here are a little more compressed. So it's not the actual air overall that's moving when you hear sound. It's air molecules that are vibrating back and forth. So that's why wind is not sound. Wind is just air moving from place to place. As an example, if you were seeing these smoke ring machines, then essentially they just create a ring of smoke. And that's an example of just like a bulk, this kind of ring of air that's moving overall, and you don't actually hear that air ring, right? Because all it is just air moving from one place to another. If you're asking yourself, well, why do I hear the wind sometimes? It's a fair question. So basically, when you're hearing the wind, what you're generally hearing is either the wind that's maybe started to vibrate some leaves or grass, right? Or so the point is that the wind is starting to push on something, and that something starts to maybe move, and then it's kind of the furthest it can move, so it pushes back, and then the wind keeps pushing it, so it pushes back, and so you start to vibrate something, and there we have that, just like the tuning fork, you start to make these sort of compression waves that move away from that thing that's vibrating, and that can actually be interpreted or can become sound, right? If it's at the right frequencies for us to hear. The other example is actually more similar to the guitar string that sets up vibration inside of the cavity of the guitar, or the body of the guitar. So another thing happens when wind rushes over your ears in the right direction and at the right speed, it can sort of set up a resonance where the air inside of your ear actually starts to vibrate back and forth. And then you can actually hear the wind. But the wind itself is the thing that's rushing by you. It's the fact that it rushes by in just the right way where it starts to kind of cause a pseudo sort of sound where you hear the air molecules right in your ear cavity sort of vibrating. Okay, so then let's just see, we have a couple of questions here. They might seem a little bit out there, not necessarily exactly what's come up in the beginning of this topic, but it kind of hopefully ties together some stuff from the last topic, from the last lecture, and actually from a previous part of this course. So go ahead and hopefully hit pause, take a second, write down an answer, and yeah. Okay. Do light waves have energy? Well, I didn't harp on this too hard in the last lecture on waves, but one of the first things I said about waves, or told you guys about waves, is that all waves carry energy. They're all be able to transfer energy in one way or another, right? So yes, light waves carry energy, or have energy. So what do you call the type of heat transfer that occurs when light transfers energy? Well, if you recall from our discussions of heat and heat transfer, one of the three types of heat transfer was radiation. And radiation was transfer of heat via light, electromagnetic waves. Coming kind of back full circle around to the fact that now we're imagining, or we're kind of understanding a little bit better, maybe what, or just understanding more about waves in general now, and how light is a wave, and as light being a wave, it carries energy, and that energy specifically is what we call radiation. radiation. Do sound waves also have energy? Darn right they do. Yep. Just like all waves, sound waves carry energy. And one of the easiest ways to see that, or understand that, is like at the very end of the last lecture, we talked a little about shock waves and sonic booms, right? And if you've ever seen a very large explosion or been near something that produces a very, very intense sound, right, you can actually feel that pushing on you. Right? So you can feel that that's a way of experiencing the energy that sound waves are carrying. Going back up to an example of light waves carrying energy, well, obviously heat radiation is energy, and there's all different examples of that. But one of the ones that everybody's familiar with is if you are standing in the shade, you feel kind of cool, maybe depending on the temperature of the day. But if you're not standing in the same shade, you're standing in direct sunlight, and you're getting all that light from the sun, you're getting all that radiation, and you heat up quite a bit, right? You feel that light, or the energy that light is carrying and dumping into you. Alright, so talking a bit about what sound is, how sound is created, but how do we interpret sound? How do we hear sound? Right? Here we have a little diagram of the human ear, and I'll just go through a little step process. This is like an overview, basically, of how we interpret, or how sound pressure waves end up being interpreted as sound. As with just about everything we talk about, we go a lot deeper into the process here, but this is a descriptive course, so we're not going to go too far into it. All that said, I'm not going to play this video, but if you want to see a little bit more in-depth look at this, and also this is where that image is taken from. It was a screen capture basically from this video. There's a pretty nicely laid out description of how the ear works. Right? So check out that video on YouTube if you want to see a little bit more detail. So basically, there's sort of three main parts of the ear. You got the outer ear, the middle ear, and the inner ear. And the outer ear is essentially, it's sort of just like a funnel. Right? So when sound comes in, you have those pressure waves, right? That movement, like compression and decompression parts of air that are kind of traveling along. When they come into your ear, right, they travel into your outer ear. They're funneled towards the middle of the ear, and first they hit the eardrum, right, which is basically like a little tiny drum head, right? And so the pressure waves are actually going to when the pressure sound waves come in, they're increasing and decreasing pressure areas. So you have the pressure that's increasing and decreasing against the eardrum, pushes the eardrum in and out. So that movement of the eardrum is connected then to these three little bones that essentially just combine together to sort of be like a lever arm, and they kind of wiggle back and forth as the eardrum gets pushed back and forth. Finally, that wiggle vibrates the fluid inside of this sort of shell-like structure, which is called the cochlea? Something like that. But essentially it's like this like snail shell looking structure, and inside of that structure is fluid, and there's also tiny little hairs all on this inner surface of that. Right? And so the movement of the bones starts to vibrate the fluid, and the fluid then starts to vibrate the little tiny hairs inside of there, and those hairs are essentially then what starts to trigger electrical impulses. So the movement of the hairs is essentially kind of it's almost like turning on and off a switch. And so the light starts to flicker on and off, and you get these electrical impulses that then travel along these nerves that then finally are transported to the brain. And so the brain gets those electrical signals, is then interpreted as, oh, I just heard a sound. So again, very basic sort of look, but yeah. From that, we can kind of understand maybe why your own voice tends to sound weird if you ever heard your own voice. And that's basically because, for the most part, when you hear yourself speaking, the majority of the sound that I'm getting from my own voice is not from the sound waves that are going out of my mouth and wrapping around to my head, or to my ear, most of the vibrations that I'm getting in my inner ear and my middle ear are traveling actually through the tissue and the bone from where my vocal cords where they're producing those vibrations. So the stuff that I'm interpreting as a sound is not actually from the sound waves, this pressure waves that are coming around. It's actually more from vibrations that are transferring inside of my skull. So that's why I think you generally tend to get a lower pitch sound. But it also just sounds different overall. So it's sound traveling through a different medium is going to sound a little different. If you've never heard yourself talk, then you could leave yourself a voice message and listen to it. Or, I don't know, listen to your own social media post if you're talking to your own social media post or something like that. Right? But most people at this point have probably heard their own voice, and yeah, it sounds odd because that's not generally how you hear your own voice. Okay. So something else about sound in general is, what we would just call loud, or interpret as the loudness of a sound, right? And so how does that relate to sound as being a longitudinal compression wave? The short version of it, or the very basic version of it, is that the loudness is directly correlated to the amplitude of the sound wave. And remember, for a longitudinal wave, the amplitude is basically a measure of the peak pressure in that wave. So for these diagrams here, we have two different sound waves. You can imagine that those compression areas are traveling from left to right, so the wave traveling from left to right. But regardless of that, if those blue dots are all essentially the air molecules visualized, right, then on the left side, the compression regions, you can tell it's a higher pressure with a lot more air molecules together in those regions. But the compression is much less than in the loud sort of picture here on the right side, where all those air molecules are even more squished together inside those compression areas. Right? That is to say that the wave on the left has a lower amplitude than the wave on the right. So these waves are in representing air molecules, and the frequency of these waves is within our hearing range. All of that. Then the wave on the left is going to be much quieter than the wave on the right, because it's directly correlated to that peak pressure in the compression wave. Let's see, I think I have a little visualization of this. So this is the best sort of visualization I could find. It's actually sort of going maybe in the opposite direction that we're talking about, when we're thinking. But if you imagine these are two different waves, right? And on the left, we're actually seeing the compression waves. So we're visualizing those little dots as the air molecules, right? And those peaks, those wave fronts, are traveling from left to right, and the waves, the particles that make up the wave, the particles that make up that sound wave are just that air molecules that are vibrating back and forth. And when they hit this sort of membrane, or this maybe drum, you can think about it could be like an eardrum. When they hit that, then the ones that have a higher peak pressure are actually moving that membrane a lot more. Right? There's a greater pressure that's being put on that membrane, so there's a greater movement, right? So that's sort of showing that the amplitude of that wave is larger, the movement that it causes is larger, versus this quieter wave where there's much less of a peak in pressure. You get much less of movement in the membrane, or in that drum end. And what's shown on the right here is essentially just the pressure that membrane, that movable surface is experiencing. Well, the pressure and also the amount of movement that it is. So that's why the pressure is directly correlated to the amount, that amplitude of the wave, and then also the volume of the wave. Right? So if these were both, say, like your eardrum and listening to different sounds, when your eardrum's moving a lot more, it's a lot more intense sound, it's a lot louder sound, so interpret as a louder sound, versus the down here might be somebody whispering at you. So we talked a lot about different sounds, but when it comes to describing the loudness of a sound, we could talk about it as the pressure, the peak in pressure, but it turns out those numbers aren't very nice, for one, and it also turns out that the change, given that the human ear can hear anywhere from a frequency of 20 hertz to 20,000 hertz, there's a extremely large change, relative change in the pressure that those sound waves can have. Usually, or so what we've done is created a different scale to represent the loudness of sounds, and that's what we call the decibel scale. The decibel scale, for one, it's not a linear scale, meaning like a change of 1 decibel is not a change in, say, like 1 Pascal, 1 pressure unit. It's a logarithmic scale, meaning that, say, like a change of 1 decibel is maybe a change of like 10 Pascal. These numbers aren't exact. It's just showing that for a small change in decibels, it's actually represents a very, or can represent a very large change in pressure. Yeah. So that in that way, it's similar to something you might be more familiar with is the Richter scale, or the scale that we use to represent the severity of earthquakes. The Richter scale is also a logarithmic scale, meaning that an earthquake that's, say, a 6 on the Richter scale is much, much less severe than an earthquake that's a 7. And even more so, a 7 is much less severe than an 8. Right? So like a change in 1 on the Richter scale is a huge change in actual severity. Similarly, a change on the decibel scale can be a very large change in the pressure. The decibel scale, we just kind of started out as being 0 as sort of like the minimum amount of sound that a person can hear. It turns out people who have very good hearing, well beyond most people's hearing, can actually hear below 0 decibels. That's if you have incredibly good hearing. But essentially 0 is sort of like the average that anybody could hear, the lowest you could hear, and the scale goes up. So we have all these examples of things. Your television might be like a 30 decibel scale. Normal conversation, maybe like when you're close to somebody, 60 decibels. I guess the television depends on the volume. Go all the way up to like when you're in traffic, maybe 90 decibels, and all the way up to something like fireworks and like rock music concerts. You get up to that like 110, 120, and that's when the decibel scale it starts to actually become, they call it the threshold of pain, but depending on how sensitive your ears are, it might not be painful or not. But regardless, it's kind of that area where the sound, the amount of that pressure that's moving your eardrum can actually start causing damage. So that's why generally people who listen to things that are very, very loud, eventually their hearing goes out. So right, so we've been talking about just sound, and that was just talking about the loudness of sound, or the amplitude of the sound wave. In the last lecture, we talked about some of the other properties of waves, one being the speed of a wave. And I told you in that lecture that the speed of a sound wave is about, well, I think it might have had 330 meters per second. This one says about 340 meters per second, but it's around there. So yeah, I mean, that's still pretty quick. And that's something like, it's a bit over 700 miles per hour, right? Another way of translating that is essentially sound will travel 1 mile in about 5 seconds. I also talked about the speed of a light wave, and that was something like 600 million miles an hour. So, a million times faster, basically, than a sound wave. And the difference in the speed of these waves is actually one way that you can get an estimate of how far away a lightning strike is. Essentially because when the lightning strike happens, it's the light that you see, the way that you see the lightning strike is light emanating from the lightning. Sound also gets emitted from that thunder, from the boom, the thunderclap. And both those things are emitted at the same time from the lightning, but the fact that the light travels incredibly fast and the sound is pretty fast, but much, much slower. It takes a little while to get to you. Right? So essentially, light travels so fast that it basically gets to you instantly. Unless you're starting to get into like planetary scales or solar system scales, light essentially gets from one place to another instantly. But it takes the sound about 5 seconds to go every mile. So that's why when you see a lightning strike, you start counting 1, 2, 3, 4, 5. You count to 5, and then you hear that thunder. That means the lightning strike happened about a mile away. Keep counting, every 5 seconds, it was another mile that was away. Alright, so some other properties of sound, and actually waves in general, but we're just going to talk about in terms of sound, is that sound reflects, just like waves, just like an ocean wave when it rolls up to the shore, reflects and rolls back out. Or in some of those other earlier demonstrations, if you have a string attached to a wall and you jerk the string up, you vibrate it up really quick and come back down, then that vibration will travel as a wave along the string. If it hits the wall that it's attached to, it will then be reflected back at you. So sound, also being a wave, reflects off of surfaces, and it's the same idea. It's a surface, it reflects, and if it's coming, say, down at one angle, it'll come back off at the other angle. If it's coming straight at a surface, it'll reflect back, that sort of stuff. And basically sound, if it's reflecting off of a rigid surface, a very stiff, very hard surface, then it reflects pretty strongly, meaning that as much of that wave, sound wave that went in, essentially comes back out. Versus if you sound hitting sort of softer surfaces, the softer surfaces, instead of being rigid, so when the pressure wave hits, it just bounces right off. If a surface is a little bit softer, then when the sound wave hits, the surface gives a little bit and it sort of absorbs a little bit of the energy of the sound. So when that wave comes back off, there's a little bit less energy coming off, and so the sound's quieter. So this is one reason why after fresh snowfall, I'm very used to snowfalls here in California, but if you've ever been to fresh snowfall, it's very quiet outside, or it seems very quiet outside. And that is because, not just because the snow is sort of like it gives a little bit, it's not super rigid, it's also the fact that the surface of the snow is very irregular. It's all these tiny little bumps and whatnot. So when the sound hits, it's not hitting this nice flat plane, it's hitting something that's like basically a very jagged sort of surface, and it can bounce in all different sort of directions and kind of disperse more. Okay, so on that same note about sound reflecting off of rigid surfaces versus softer surfaces, we take a look at these pictures here, and they're both two restaurants maybe, and even though there's only people in one of them, you can imagine that both these places are filled with people. Which one do you think would be quieter? So take a second to think about that in terms of, again, reflection of sound waves. Alright, so hopefully you recognize that the left image, the walls of the restaurant are brick. Brick is stone basically. It's a very rigid, hard surface. Right? So when the sound hits those walls, it reflects off and doesn't really lose any energy. So basically just as loud as the sound was that went in, as loud as it's going to be when it comes out. Okay, so that was one way that waves can sort of be changed or sort of affected by the things they encounter. That was reflection. So reflection, we're going to keep it in mind, it's just like, you see your reflection in the mirror, you're looking straight at the mirror, your reflection comes straight back out at you. Right? Reflection of waves and sound waves in particular off surfaces, if they come in at one angle, then essentially they come out at the same angle on the other side. And other waves do the same sort of thing. Right? So that's reflection. The other kind of way that waves will interact with things that are around them is what we call refraction. So refraction isn't a wave necessarily running into something and bouncing off. That would be reflection. Refraction is when a wave encounters a change in the medium that it's moving through. Right? So for sound is traveling through air, and if sound travels through air and it gets to a place where the air is warmer, right? It's still the same medium, but the air is different there a little bit, right? So when the medium that the wave is traveling through changes, or when the wave travels and starts to go through a new medium, then that wave will typically bend in one way, right? So instead of going straight and like reflecting, like a reflection, if it's going, and this is maybe say a new medium that the sound is going to pass into, it might bend in a certain way. In terms of sound and sound traveling in air, it turns out that sound will travel faster in warmer air. And you can think about that as if you remind yourself about how gases like air, when they're warmer, generally there's more pressure, there's more air molecules closer together. Right? And since sound is just a movement being transferred from one air molecule to the next, when all the air molecules are close together, it's easier for the sound to pass along. So, for example, if you are speaking, like in the picture we're showing here, this guy is playing a trumpet or something like that, and in one case, on the top here, the air right near the surface is very warm, and the air above is cool. Right? So in that case, the sound travels quicker through the warmer air and slower through the colder air. So you can imagine it's like two wheels of a car, where the one wheel is going a little bit slower than the other wheel. That means the car is going to start to turn. Right? This one's going faster, so it's turning. It's going more revolutions, going further. It's causing the whole thing to start to turn. Or in this case, but in this way, this wheel is going a little bit faster, so you start to turn that whole thing. So that's why the sound wave will tend to travel upwards a little bit when the air is warm below and cool above. And then conversely, if the air was warm above and cool sort of closer to the surface, or closer to the ground, then the opposite sort of thing will happen, right? Where the sound's traveling along and the air above is traveling a bit faster, the air below it, so it starts to sort of bend down. Right? And these are both examples of refraction. One's refracting sort of upward, one's refracting downward. One example of this happening is over like a lake. If you've ever, or a big pond or something like that, you might have noticed that you can hear people very far across the lake, much further than if you were just talking, or they were far across a field or just an open ground area. And the reason that is generally that the air is very cool just above the lake, or just above the lake's surface. So when somebody speaks, the pressure waves, right, the sound waves that they're creating, don't just start to kind of dissipate and go up into the air and move up around everywhere. They kind of more get directed down along the surface of the lake, and in that way end up staying sort of more concentrated along the surface, and so they can kind of travel very far along the surface of the lake until they get to the far shore and start to kind of move back up again, and you can hear them. So finally, let's get into talking about music as a particular kind of sound, I guess. And just to begin with, there's a difference essentially, or a distinction that we make between just noise and music. In some cases, that distinction is fairly arbitrary and very subjective. People might argue that some kind of music is just noise, but we're not going to worry about that exactly. Right? There are gray areas, but in general, noise, or like white noise, is going to just be kind of a sporadic sort of variations in pressure. Right? So it's still noise, it's still sound, because it's these sort of variations in pressure, and it's this compression wave that's being created by something or other. But if we were to look at the pressure, or the way that pressure increases and decreases over a certain area, the wave travels along here, there's no real structure to it, or well, we wouldn't say that it's it just doesn't look very nice. There's no repeating sort of nature to it. It's not periodic. It doesn't. You know. So this is more of a picture of what sound might look like that we just call white noise. Versus music, we typically think of as being noise, but also noise that's periodic. It doesn't have a whole lot of, or not always, it doesn't usually have a whole lot of just random things going on. So if we look at the pressure wave, or the diagram of the pressure of musical sound wave, then essentially it looks much prettier. It's just a sort of nice, periodic looking, smooth change up and down. Right? Maybe you have these little wiggles along the top of the wave and then come back and move again. But the main thing that really distinguishes just regular sound from music is that music has this sort of periodic nature about it. So we're going to talk a bit more about sound, about music. And before we get too much into that, I should really point out that while I really enjoy music, I'm certainly not as specialized in any way in the details of music and theory and things like that. So this is very much a physicist's interpretation of music, and it's going to be very broad strokes. Yeah, so we're just going to look at some of the broad characteristics. And generally speaking, there's sort of three, these could be a little bit different, but I'm just going to break it into these three sort of characteristics of sound, or musical sounds. Right? So one is what we call the pitch, and pitch, if something's high pitched, it's hard to say anything else, it's high pitched, right? Or low pitched, very low tones, high tones, low tones. So the pitch is telling you sort of the highness or the lowness of the sound. And essentially, in terms of the wave, the pitch is basically determined by the frequency of that sound wave, the pitch of her musical note. And we'll get into those variations on that, or complications on that, but essentially it's like this sort of fundamental frequency of that note is what determines its pitch. Another characteristic is intensity, which we've kind of already talked about in terms of just sound in general, but intensity is essentially a measure or saying how loud a sound is. And then finally there's quality, which is probably the most complicated of the three, in that it has to do with something called harmonics. And those are, well, we'll talk about it more, but essentially quality is saying how pure of a sound is that, like how few frequencies make up that sound. So first off, talking about pitch, right? The simplest examples of differences in pitch, we're just thinking about the differences of the sort of base musical notes. Usually we talk about the sounds that make up music as broken down into these notes, A, B, C, D, E, F, G, and each of those notes has a certain frequency attributed to it. So for instance, C, the first C, or C, I don't know how a musician would say it, but the fundamental C note is a frequency of about 32 hertz. And again, obviously I'm not very familiar with music because I don't know how the other notes relate to that. But each of those other notes has a particular frequency that it's associated with. And it turns out that you can play that same note, that's what's known as a different octave, if you play a multiple of that frequency. So if the fundamental C is about 32 hertz, then the next octave up is going to be twice that frequency, so about 64 or 65 hertz, right? The next octave up above that, about 130 hertz, right? So that first one, that 32 hertz, that's that fundamental frequency. These other octaves, these multiples, are also called, in physics we call them harmonics, right? So multiples of that fundamental frequency. And so also recalling that for a wave, the frequency is saying how quickly that wave sort of goes through a full oscillation, right? So if we're looking at or imagining the sound waves, right, it's the movement of air. It's like you can imagine that one frequency, say that 32 hertz, that fundamental C note, is maybe air moving like this, that sort of frequency, versus maybe a few octaves up there, the air is moving a lot faster. It's a much higher frequency. Right? So much higher frequency is essentially much more rapid movement overall. And I guess a standard piano covers about 7 octaves for each note. And then, I'm not even sure, I'm not a musician. I think the black keys are sort of in between any of those fundamental notes. I'm sure some of you know that, but I don't. So the next characteristic was loudness, or the intensity of the sound. And again, we kind of already talked about this, where the intensity of the sound is basically related to the amplitude of that sound wave. And again, in longitudinal waves, like sound waves, the amplitude is a measure of the peak pressure in the wave, right? Or how high does that pressure get on the wave. So that's sort of basis is just how high, what's the pressure in that wave, right? But it turns out that the loudness of a sound is actually not just dependent on the peak pressure, because the loudness in a way is dependent on how our ears have evolved to interpret sound. And it's not just essentially how much the eardrum will move, so that would be sort of determined by the pressure in the wave, just the amplitude of the wave. But our ears are more attuned to pick up particular frequencies, or maybe easier to tune into different frequencies. So even though we hear frequencies from, say, 20 hertz to 20,000 hertz, there are some areas of that spectrum where our ears are just more adept to absorbing them, maybe think about it, interpreting them. So all that is to say that you can have a sound that is 80 decibels, remember, and people call it decibels, was a measure of the pressure of that wave, right? So decibels, both 80 decibels mean they're both the same pressure. But if one of those sounds is at 3,500 hertz, it turns out that's going to sound almost twice as loud as a sound with a frequency of 125 hertz. So, and that is because our ears are designed or made up in a way, or work in such a way that they're more sensitive to that frequencies around that 3,500 range. So it turns out that the loudness of the sound is, yeah, for one, it can be measured by the peak and the pressure of that sound wave, but it also turns out that due to the way that our ears are have evolved, there's particular areas in our frequency ranges that are just more sensitive to overall. So it's sort of a combination of those two things. Okay, finally, quality. Right? So like I was saying earlier, quality is essentially, one way of saying is how pure a musical note is, or how pure a musical sound is. So you can get an idea of what quality is if you say, listen to a piano playing that, say, that fundamental C note at 32, 33 hertz C. So a piano can play that sound, play that note, but a clarinet can also play that same note, and they sound very different, right? Well, they sound very similar in a way because they're playing that same fundamental frequency, but you can also tell that they're not played by the same instrument, right? There's certainly a difference. I have a terrible ear for sound, so I could probably not even tell you they're playing the same note. That's because I guess my ear is more attuned to pick up quality rather than the musical note. So another term that I guess gets used for this is the color of the tone, the timbre. Yeah, and so it seems like timbre is sort of another way of saying quality. This is a little bit confusing for me in some of these terms. And essentially it's sort of a catch-all for things that aren't included by pitch that we already talked about, loudness, and one other characteristic that I didn't really talk about was just the length of the tone, just how long you hold that tone for. Yeah. Okay, so why do two different instruments that are playing the same note sound different? Well, again, it depends on the quality of that sound, and the quality, again, is a measure of how pure that tone is, or how pure that pressure sound wave is. So, as I mentioned before, when we're talking about different musical notes, you have, say, one musical note, say, again, we'll just keep harping on that C note at, say, like 32 hertz. If we were to represent that as a vibrating string, then we could say that that first C note is this fundamental harmonic, and you've got to imagine that this guy is just vibrating up and down. You know. If we were to double the frequency of this vibration, then we'd end up getting a picture like this, where this is now that 64-ish hertz vibration, that second C note. We triple that frequency, we get this sort of picture where we have this third harmonic. Quadruple it, you get the fourth harmonic. So these are all different versions of that same C note. They're just different, we call harmonics of that C note. Or in music, different octaves. When you have an instrument, say like, think about this as like even a guitar string. Maybe you pluck a guitar string, maybe the whole guitar string is moving up and down and you're just getting that fundamental frequency. But more often than not, it's not just moving up and down. It might be moving up and down like this, but also vibrating maybe at that third frequency as well. So even though the string's going up and down overall, inside of that movement, there's this third harmonic that's happening as well. So this picture down here is essentially a combination of this fundamental harmonic and the third harmonic. Right? You kind of put those two together, we get this picture. So this could be an example of a guitar string that's vibrating at a C note, but it's a combination of that fundamental C. A little bit more about quality. As we saw on the last slide, that quality is essentially a measure of how many different sort of frequencies are overlapping on top of each other. So this is why, say a piano playing a C versus a clarinet playing a C note is distinguishable, because even though the fundamental frequency that they're both playing is C in these pictures, that fundamental frequency is that overall arching sort of shape. Right? It comes up and down, and it happens at the same frequency in both of these cases, so it's the same fundamental note that's happening. Both of them have this overarching sort of shape that's happening at the same frequency. But the clarinet, well, for one, it looks like there may be more higher frequencies, higher harmonics on top of that frequency. And yeah, it's mostly probably just that. There's, instead of, in that last slide, we have a picture where there's that first harmonic and the third harmonic overlapping. This is an example where you have first harmonic and third harmonic, fifth harmonic and 12th harmonic, 13th harmonic, right? You have a bunch of these harmonics stacking on top of each other, and you end up getting a wave, a sound wave, that has a lot of these more sort of jagged regions on this up and down motion. Where the piano would have that too, but it just has a bit less of that. Our ears are attuned to hearing these subtle differences in those, having those higher harmonics present or not. So all that said, color quality, and I was saying it as a measure of how pure a tone is. It has nothing really to do with how nice a tone is or how good it is, right? All that has to do is an interpretation. It's a subjective call. You like a certain kind of music, or you don't like it. So these are just ways of being more consistent and particular about how we talk about music. It's not to say that one kind is better than another. Right. So that's all I got for this lecture on sound and music. There's much more to say right now. I guess I'll just end there and say best wishes again to you all, and hope you're doing well.